A Soviet sonar operator's screen shows empty water. Above him, 80,000 tons of American steel is closing at 17 knots. In 90 seconds, K-314 will surface directly into the USS Kitty Hawk's hull, and both captains will realize the collision they just survived could ignite a crisis if either side escalates. The impact causes severe damage to the submarine's propeller and hull. Soviet accounts maintain the reactor compartments remain secure, though the loss of propulsion leaves the vessel crippled. And before the crew can even process what hit them, both nations make the same calculation. Downplaying the severity avoids diplomatic catastrophe. But keeping tensions low requires something extraordinary. The Soviets have to tow a submarine with significant hull damage 400 miles through waters crawling with American destroyers, in total radio silence. The Americans have to carefully manage what their sonar operators report. 100 Soviet sailors have to survive the tow. Without surfacing, without communicating, without any guarantee their hull won't fail at depth. While both governments publicly acknowledged the collision within hours, the full extent of the damage and risk remained unclear for years. The question isn't what happened in those 90 seconds after impact. It's what both captains understood in that moment that made minimizing an active war seem like the safer choice. It began because the sonar operator trusted his training over his instincts. Soviet doctrine said if the screen is clear, the water is empty. The screen was clear. The water was not empty. And by the time he realized his instruments were lying, the hull was already screaming. K-314 had been shadowing the Kitty Hawk battle group for days, maintaining depth at 180 meters. The Victor-class submarine's mission is to log the carrier's position, speed, and escort pattern during Team Spirit exercises, the largest U.S.-South Korea war games of the year. The captain's hydrophones pick up the rhythmic churn of destroyer screws, the high-frequency ping of active sonars sweeping the perimeter, but nothing directly above. The Sea of Japan thermocline sits at 120 meters this time of year, a sharp temperature boundary where warm surface water meets cold, deep water. Sound waves bend downward at that boundary, just as light bends in a lens. Anything above the layer is invisible to passive sonar below it. The captain needs a visual fix to update Moscow on the carrier's exact heading. The captain gives the order. Rise to periscope depth, slow ascent. The diving officer repeats the command and opens the ballast tank valves. Compressed air hisses into the forward and aft tanks. A sound every submariner knows means you're either escaping the deep or about to be detected. Seawater forces out through vents in the keel. The submarine weighs 5,200 tons submerged, and to rise, it must displace enough water to reduce that weight by 500 tons, achieving neutral buoyancy. But right now, what matters is the hull groaning as external pressure drops from 18 atmospheres to 1. Metal frames creak in protest. The depth gauge unwinds. 160 meters. 140. The crew feels the deck tilt upward 3 degrees. No one speaks. This is routine, performed dozens of times on every patrol. Routine, until it isn't. The sonar operator keeps his eyes on the screen, still empty overhead. The hydrophones of K-314 should pick up the carrier's propellers. 4 massive bronze screws, each over 20 feet across, churning through the water. That should generate a broadband signature audible for 20 miles. But K-314's own machinery drowns it out. The reactor's coolant pumps and other systems generate tremendous noise. Air circulators hum. The ballast venting roars through the hull. All of that noise saturates the passive array, masking faint signals from above. Active sonar would cut through the clutter instantly, a single ping reflecting off the carrier's steel hull. But active sonar announces the submarine's position to every destroyer in the battle group. Protocol forbids it, except in self-defense. The submarine remains acoustically blind in the final 60 meters of ascent. 60 meters depth. 90 seconds from the surface. The captain orders the diving officer to slow their ascent, maintaining stealth as they approach the surface. A controlled rise means less turbulence when they break through, less chance the periscope wake will be spotted by lookouts on the carrier. The diving officer adjusts the trim, venting air in short bursts to fine-tune buoyancy. 30 meters. The hull is lighter now, external pressure reduced as they climb. The officer commanding watches his display one last time. No contacts within 500 meters. The water above is clear. As they reach periscope depth, the sail approaches the surface, the tall vertical fin that houses the periscope and radar mast. Then the captain will raise the scope for a 60-second visual sweep. 12 meters. The officer leans back. The screen is empty. The Sea of Japan thermocline is not a myth. It's a trap. Water temperature plunges 6 degrees Celsius in just 10 meters of depth. Sound velocity in water depends on temperature. Warmer water carries sound faster. When a sound wave traveling upward hits the thermocline, it bends downward, refracted like light entering glass. But here's what K-314's commander doesn't know he's trusting his life on. Passive sonar hydrophones mounted on K-314's hull, below the layer, cannot detect propeller noise from ships above it. The physics is absolute, and absolutely blind. A carrier steaming directly overhead is invisible unless it crosses into the cold water below 120 meters. Kitty Hawk draws 38 feet, about 11 meters. It never penetrates the layer. For the Soviet captain, the acoustic picture is honest. The screen shows what the hydrophones hear. Nothing. He believes the silence. He believes he's alone. The thermocline doesn't lie, but it doesn't tell the whole truth either. Victor-class submarines carry no upward-looking collision avoidance sonar. Available records suggest the Design Bureau operated under the assumption that a submarine ascending slowly in open ocean would never encounter a surface vessel. Statistical probability favored the assumption. The Pacific spans 64 million square miles. A carrier battle group occupies perhaps 50 square miles. The odds of a random ascent intersecting a surface ship are vanishingly small. Soviet naval doctrine in 1984 does not require fathometer checks during ascent in international waters. The crew trusts passive sonar, and passive sonar trusts the thermocline. No one aboard K-314 questions the empty screen because the system is working exactly as designed. It is detecting everything the physics allows it to detect. The failure is not in the equipment. It is in the assumption that the equipment can see everything that matters. A single active sonar pulse would solve the problem. The submarine's MGK series sonar array can transmit as well as receive. One ping, traveling upward, would reflect off the Kitty Hawk's hull in less than a second. The return signal would show range, bearing, and speed. Captain Evsenko would see the carrier on his screen, bright and undeniable. He would abort the ascent, dive to 200 meters, slip away. But Soviet protocol strictly limits the use of active sonar to maintain stealth. A ping travels for miles, lighting up the submarine's position for every destroyer in the battle group. In a combat scenario, American ASW Doctrine could call for an aggressive response to active sonar contact in a carrier screen. K-314 could expect a counterattack within minutes. Soviet submarine protocol accepts acoustic blindness as the price of stealth. It is a calculated trade, survival over certainty. Evsenko does not activate the transmitter. The captain's hand rests on a frayed binder. Soviet submarine procedures, the kind refined through decades of Cold War patrols. The principle is straightforward. When passive sonar shows no close contacts during ascent to periscope depth, proceed with visual observation. He's done this hundreds of times. These procedures evolved throughout the 1970s, shaped by countless North Atlantic and Pacific patrols. It's muscle memory now. The manual assumes the thermocline problem is known and accepted. It assumes commanders will use periscope sweeps to fill the acoustic gap. But here's what it doesn't account for. A carrier, steaming at high speed, directly above a rising submarine. Why would it? No carrier commander would knowingly position a ship over a hostile submarine. The doctrine is sound. The assumption, the fatal assumption, is that the other side will not be blind at the same moment. 60 seconds from now, that assumption fails. For both captains. Simultaneously. The sail breaks the surface. 23 feet of steel fin housing the periscope, radar mast, and snorkel. The submarine surges upward in an emergency blow, rising into the Kitty Hawk's hull, which is moving at 12 knots, 6 meters per second, sideways. The sail hits the carrier's starboard quarter, a glancing blow, but violent. According to some accounts, the periscope mast shears off, the radar antenna crumples. Yet, the submarine's captain would later report that his masts and antennas remained functional after the first strike. The sail's leading edge, hardened steel 2 inches thick, absorbs tremendous force against the carrier's hull plating. Then the impact transfers downward, through the sail frame. Dramatic reports describe ruptured forward ballast tanks, massive flooding in seconds, the submarine lurching bow down, deck tilting 15 degrees. But official Soviet damage assessments told a different story. The catastrophic failure was the propeller, mangled beyond use. Emergency alarms scream. The captain, Vladimir Evsenko, is thrown against his console. The impact has caused severe structural damage to K-314's stern section. The collision likely compromised hull integrity, though the exact extent of internal damage remains unclear from available records. Systems throughout the submarine are failing. The diving officer struggles to regain trim as control surfaces fail to respond properly. The submarine cannot maintain its pitch angle. The captain orders emergency surface, full ballast blow. Compressed air roars into all tanks simultaneously. K-314 surges upward, breaking the surface completely, hull rolling in the swell. The reactor scram alarm sounds. Automatic shutdown triggered by the sudden depth change. They have no propulsion, no diving ability. They are fully surfaced in the middle of an American carrier battle group. On Kitty Hawk, damage control alarms sound in 4 compartments. The impact occurred on the starboard side near the bow, potentially affecting machinery or fuel spaces. The hull breach, 15 feet long, sits below the waterline. Seawater floods in rapidly. Damage control teams, led by senior enlisted personnel, respond immediately to the breach. They see the gash, steel plates buckled inward, the roar of incoming seawater. They order collision mats and wooden shoring. The compartment must be isolated before the flooding spreads to the adjacent boiler room. If the boilers flood, the carrier loses propulsion. A dead carrier in hostile waters is a target, not a weapon. Following the impact, Kitty Hawk's sonar room identifies a surfaced submarine contact alongside the carrier. The sonar officer confirms it as a Victor 1 class Soviet Pacific Fleet. Propeller signature matches known profiles. The submarine appears dead in the water, its propeller cavitation gone. The carrier's commanding officer, Captain David Rogers, receives the report on the bridge. He has just felt the collision through the deck plating, heard the alarms, and now sonar confirms what he already knows. He has struck a Soviet submarine. There is no direct communication channel to the submarine, no encrypted link to Moscow. Communication with higher command in such a high-stakes encounter would be notoriously slow, potentially taking over an hour to relay through established Cold War channels. Rogers must decide in minutes whether this is an accident or an attack. Rogers faces an immediate decision as escort destroyers monitor the situation. Under standard ASW protocol, a hostile submarine surfacing within a carrier screen could trigger defensive measures to neutralize the threat. The destroyer captains await guidance from the carrier commander. If he were to declare hostile action, the destroyers could bracket K-314 with depth charges, potentially sinking it in minutes. If the submarine carries nuclear torpedoes, and the crew believes they are under attack, they may launch before sinking. One nuclear torpedo, 15-kiloton warhead, detonated under the Kitty Hawk's keel, could break the carrier in half. Rogers does not know if the submarine is armed. He does know that attacking it will force Moscow to respond. The question is not what happened. It is what happens next if he chooses wrong. The bow is going down. Substantial amounts of seawater flooding K-314's forward ballast tanks in seconds. The crew feels it. The deck tilts beneath their feet. Here's what likely happened. The impact occurred along the upper hull and propeller, causing structural damage that compromised the submarine's outer frame and ballast tank integrity. These are steel chambers integrated into the outer hull structure, situated between the light outer hull and the reinforced pressure hull, designed to hold compressed air at 20 atmospheres during deep dives. Structural welds failed across a significant portion of the forward hull. The ocean poured in instantly. A submarine achieves neutral buoyancy by balancing its weight against displaced water. That balance just shattered. The bow is being dragged down. And now K-314 faces an impossible trap. They cannot dive. Compressed air vents through the cracks as fast as it's pumped in. The ruptured ballast tanks won't hold pressure. Diving requires neutral buoyancy. Neutral buoyancy is impossible with ruptured ballast tanks. The submarine is forced to remain on the surface, exposed, crippled, exactly where the Americans can see them. According to some reconstructions of the incident, flooding may have spread through the damaged frame. While narrative accounts suggest seawater reached the control room bilge and forward battery compartment, official reports from both the Soviet captain and U.S. observers indicated the pressure hull remained intact. If electrical systems were compromised, the bow plane hydraulics could have been affected. The bow planes are horizontal fins mounted on the submarine's nose, used to control pitch angle during ascent and descent. Hydraulic actuators move the planes through a 30-degree range. In the event of hydraulic failure, such systems are typically designed to lock the planes in neutral position. Loss of bow plane control makes depth maintenance exceptionally difficult and hazardous. While stern planes provide primary pitch control, any misalignment in the bow planes during descent could create dangerous instability. Even if the crew could repair the ballast tanks, significant hydraulic damage would make safe diving extremely risky. The submarine was effectively trapped on the surface. The crew had no option but to wait for rescue. According to damage reports, the starboard bow section sustained impact damage. While the exact extent of internal flooding remains unclear from declassified records, damage control teams face the challenge of sealing a breach in the hull's outer plating, a breach that, by some accounts, allowed seawater to enter the forward compartments. On an aircraft carrier, flooding presents a critical threat to stability. Even moderate water ingress can shift a ship's center of gravity, creating a list that grows more pronounced as water accumulates. Sailors on the hangar deck would feel it first, a subtle wrongness in their footing, like the world tilting beneath them. Tools begin sliding across workbenches. In the spaces below, men brace themselves against bulkheads just to stay upright. At 7 degrees, the flight deck tilts enough that aircraft cannot be launched or recovered safely. Planes would skid. Arresting wires would pull at wrong angles. The ship's steel frame groans under the uneven weight distribution. Damage control teams deployed portable pumps to manage the water ingress, though the capacity of field equipment is always limited compared to a ship's main drainage systems. The challenge with any hull breach is that pumping alone rarely solves the problem. You must patch the breach itself, a procedure that requires divers, underwater welding equipment, or temporary collision mats secured from outside the hull. None of that can be done underway in open ocean. According to available accounts, a damage control team led by a chief petty officer organized a 4-team effort to deploy a collision mat over the hull breach. A collision mat is a heavy canvas tarpaulin reinforced with rubber, designed to be pulled over a breach from outside the ship. Suction from the inflow holds the mat against the hull, slowing the flooding. The procedure requires divers to attach cables to the mat corners, then pull the mat down and across the breach using winches inside the flooded compartment. Under ideal conditions, such operations can take many hours to complete. Kitty Hawk is underway at 12 knots in 4-foot swells. The divers cannot work safely at that speed. Captain Rogers reportedly ordered the carrier to proceed at a significantly reduced speed, which would extend the time to reach the nearest repair facility. Slowing also makes the carrier a more vulnerable target for any Soviet submarines trailing the battle group. The carrier's hull is hardened steel, 3 inches thick at the waterline, designed to withstand torpedo near misses. But the collision has buckled the plates inward, creating stress fractures radiating from the breach. Each fracture is a potential failure point. And here's the problem. As the ship flexes in the swell, the cracks propagate. Every wave, every turn, every second. Damage control teams worked urgently to assess the timeline before the fractures could become critical. But that assessment depended on ideal conditions. A single rogue wave, a sharp maneuver to avoid debris, even the vibration from the engines, any of these could worsen the stress fractures without warning. The ship had lost several thousand tons of jet fuel through the breach, creating significant weight distribution issues on the starboard side. Combined with the structural damage, the situation raised serious concerns about the hull's integrity under continued operations. The design safety margin is calculated for normal damage and controlled flooding. This breach, combined with underway operations, pushed the limits of what the ship was built to handle. Captain Rogers had to get the ship to the nearest naval repair facility at Subic Bay before the damage worsened, navigating carefully to avoid any additional stress on the compromised hull. The clock was ticking. But the ocean doesn't care about clocks. Rogers' immediate priority is damage assessment and crew safety. U.S. escort vessels maintain close proximity to the disabled submarine, monitoring its condition. While the battle group remains at heightened alert, available records suggest the focus was on observing the crippled vessel rather than preparing an attack. Rogers faces a calculated decision. A disabled Victor-class submarine, fully surfaced with no propulsion, poses an uncertain threat. Any aggressive action could force Moscow to retaliate, and retaliation means war. Rogers cannot know if the submarine carries nuclear torpedoes. What he does know is that sinking it guarantees escalation. The calculation is cold. A live Soviet submarine crew is a problem. A dead Soviet submarine crew is a casus belli. He chooses the problem over the war. K-314 remains on the surface, surrounded but not attacked. On K-314, the captain faces the same calculation. He is surrounded by American destroyers. His submarine cannot dive. According to available accounts, he lacks immediate secure communication with Moscow. Any aggressive action will be interpreted as an attack and will trigger immediate depth charging. He orders the crew to surface fully and open the hatch. Historical accounts suggest the crew also shut down the reactor cooling pumps. Shutting down the pumps would create a detectable signal. The carrier's sonar could pick up the reduction in machinery noise. It may have been intended as a way to communicate non-hostile intent without a radio. The reactor will overheat if the pumps stay off too long, but the captain accepts that risk. The alternative is to be mistaken for a threat and destroyed. The pumps reportedly go silent. Kitty Hawk's sonar room notes the change in the submarine's acoustic signature. Rogers observes the submarine's behavior and responds accordingly. According to crew accounts, Ramirez and his teams work the collision mat into position. Divers in the water, 4-foot swells rolling over them, attaching cables to the mat corners. Inside the flooded compartment, 2 teams operate the winches, pulling the mat down and across the breach. The suction is immense, flooding reportedly running at 200 gallons per minute, trying to rip the mat away from the winch cables. Accounts suggest it takes approximately 90 minutes to seat the mat fully. The flooding slows to an estimated 50 gallons per minute. The pumps can now keep pace. Internal damage reports indicated water level stabilizing around 12 inches. The list is holding at roughly 3 degrees. Flight operations can resume. Ramirez reports to Rogers. The patch is expected to hold for 72 hours if the seas stay calm. After that, the mat will degrade and the flooding will resume. Rogers sets course for Yokosuka for emergency repairs. Soviet Pacific Fleet receives K-314's distress signal shortly after the collision. The signal is brief, encrypted. Surfaced, unable to dive, surrounded by American battle group, non-hostile, position and status only. Soviet authorities respond quickly, dispatching a rescue tug from Vladivostok, the nearest Soviet naval base, several hundred miles to the northwest. Here's the problem. The tug, Foti Krylov, is rated to tow surface vessels up to 60 tons. K-314 displaces 5,200 tons submerged. Towing the crippled submarine requires maintaining a slow, steady speed of roughly 4 to 5 knots to prevent further damage. 4 to 5 knots. At that speed, the transit will take several days. Several days on the surface. Several days tethered to a cable already operating at the edge of its tolerance. Several days within the American carrier screen, unable to dive, unable to maneuver, hoping the Americans do not change their minds. Hoping the cable holds. Hoping no one decides. This is an opportunity. The tug departs Vladivostok within hours of the incident. K-314 must remain exactly where it is, waiting. Exposed. According to some accounts, Rogers decides to remain on station, attempting to provide assistance to K-314. The submarine's long-range communications may have been compromised in the collision, leaving only short-range VHF capability. One narrative suggests Rogers orders his signals officer to establish an extraordinary relay channel through Pacific Fleet Command, routing Soviet transmissions from K-314 through Kitty Hawk's transmitters to Vladivostok. If such a relay existed, it would represent an unprecedented step, using an American carrier as a communication bridge for a Soviet submarine. Rogers would have calculated that transparency reduces the risk of miscommunication. If Moscow cannot reach K-314 directly, they may assume the submarine has been captured or destroyed, and that assumption could trigger a military response. The alleged relay channel reportedly goes live 4 hours after the collision. Moscow is believed to have confirmed receipt of K-314 status updates. The risk of miscalculation drops, but Rogers' carrier is now stationary, a dead target if Soviet attack submarines are trailing the battle group. A Soviet rescue tug arrived within days to assist the damaged submarine. The crew passes a steel tow cable to K-314, attaching it to the submarine's bow cleats. Using heavy-duty towing equipment rated to handle the submarine's 5,200-ton displacement, the tow must proceed at 4 knots to keep cable tension below the breaking point. Any faster and the cable will snap. Any slower and the submarine will wallow in the swells, risking further hull damage. The tug begins the transit back to a Soviet naval base. Kitty Hawk's escorts shadow the tow for the first 12 hours, then peel off as the submarine crosses into Soviet-controlled waters. The American destroyers report the submarine under tow and the carrier screen intact. No hostile action from either side. Kitty Hawk limps into Yokosuka Naval Base 8 days after the collision. The collision mat has held, barely. According to damage control reports, water continued to seep through the edges as the carrier made its way to port. The flooding has resumed. March 29, 1984. The carrier enters dry dock. Inspectors assess the damage. The hull breach extends through 3 frame sections. Full plate replacement required. Welders cut away the damaged steel, fabricate new plates. 6 weeks of work. The bill? $2.8 million. For the Americans, it's a repair job. Expensive, but manageable. The carrier returns to service in May. For the Soviets, a different calculation entirely. Victor-class submarine K-314 sustained severe damage in the collision. Soviet records indicate the submarine was repaired and returned to the fleet, only to meet a far more catastrophic fate. In August 1985, during a refueling operation at Chajma Bay, a reactor accident destroys the vessel. K-314 survives the collision with an American carrier, only to be lost to a nuclear disaster 16 months later. 2 superpowers, 2 vessels, 1 collision. The Americans pay millions to restore their carrier. The Soviets repair theirs, only to lose it to their own technology. And the official record? Initial Navy reports describe the incident as a collision with an unknown submerged object. Within 24 hours, however, the Pentagon publicly identified the Soviet submarine. The full details remain classified, but the collision itself was never truly hidden. Two nations, two narratives. One acknowledged, one buried in the aftermath of nuclear catastrophe. K-314 reaches Vladivostok on April 2, 1984, after a 9-day tow. The submarine is immediately dry-docked for damage assessment. Naval records indicate the primary damage was centered on the propeller and stern stabilizer, requiring extensive repairs to the vessel's aft section. Technical reports suggest that while certain hydraulic components remained functional, the vessel required a complete overhaul of its damaged systems. Repairs lasted approximately 5 to 6 months, with the vessel returning to trials by August 1984. K-314 briefly returned to combat duty in 1985, including a deployment to the Indian Ocean, before a reactor plant failure later that year curtailed its operational career. The submarine was officially decommissioned in 1989, with the crew disbanded in 1994 and scrapping occurring in the mid-1990s. Soviet Pacific Fleet records describe the damage as the result of a collision with an underwater obstacle. No mention of an American carrier. The incident report is classified. Both governments moved quickly to downplay the strategic significance of the event, though the collision made international headlines within days. Military leadership on both sides worked to de-escalate the diplomatic fallout, even as ship captains provided initial reports in public statements. The formal response was channeled through the 1972 Incidents at Sea Agreement, the established protocol for such encounters. The U.S. Navy conducted an investigation and publicly blamed the Soviet captain for violating the accord. The Soviet Navy also investigated, ultimately relieving Captain Evsenko of command. While the collision itself was public knowledge, reported in newspapers from New York to Moscow, certain technical details remained closely guarded. The intelligence value of the incident, fragments of Soviet propeller blades, pieces of anechoic coating recovered from the carrier's bow, was kept quiet by the U.S. Navy. What the public knew was that two Cold War giants had collided in the Sea of Japan. What they didn't know was what American intelligence had gained from those few seconds of contact. The collision became a footnote in the public record, but in classified files, it represented a rare intelligence opportunity, preserved by the same calculation that had prevented escalation in the 5 minutes after impact. The collision triggers quiet changes in both navies' doctrine. The U.S. Navy revises Carrier Battle Group ASW screen procedures. Some analysts suggest a shift toward more active sonar use in contested waters to prevent collision, though the Navy's traditional emphasis on stealth complicates any such mandate. Soviet submarine doctrine is reportedly updated to require more frequent upward-looking sensor checks during ascent in shipping lanes. Some Soviet submarines are believed to have received improved obstacle avoidance sonar upgrades in the mid-1980s, though whether these were direct responses to the incident remains unclear. Neither Navy publicly explains the changes. New procedures appear in classified training manuals and are implemented without announcement. Both sides learn the same lesson. Acoustic blindness is acceptable in open ocean, unacceptable in crowded waters. The changes help prevent future collisions, though their connection to the 1984 incident is never officially acknowledged. 4 years after the collision, tensions between the United States and Soviet Union lead to renewed discussions on naval safety protocols. While the two nations had signed the 1972 Agreement on the Prevention of Incidents on and over the High Seas, the 1984 incident exposed gaps in submarine-specific protocols. By 1989, they formalized the Agreement on the Prevention of Dangerous Military Activities, which addresses close encounters between military forces. The agreements include provisions requiring vessels to exercise due regard when operating near one another and to use available means to avoid collision. Both sides understand these protocols relate to incidents like the 1984 collision, but the agreements never mention specific events. The text is carefully neutral, applicable to all navies. It becomes the framework for future naval incident management. The agreements remain in force after the Soviet Union dissolves. They are among the few Cold War accords that survive into the post-Soviet era. The collision that almost started World War III becomes part of the foundation for preventing future collisions, but only through documents that never acknowledge it happened. While the incident was reported in the press at the time, detailed operational records remained classified for decades, with partial declassification occurring in the early 2000s. Even then, full details were not released. The Navy acknowledged a 1984 incident involving Kitty Hawk and a Soviet submarine, but provided no operational specifics. K-314's records remain locked in Russian naval archives. No formal investigation was ever published. The fuller story emerged through interviews with former crew members, declassified signal intercepts, and intelligence assessments released decades later. What is clear is this: two nuclear-armed platforms collided. Both captains chose restraint over escalation, and both governments chose silence over accountability. The cover-up worked because both sides understood that admitting the full scope of the collision would have been more dangerous than limiting what was disclosed. The lesson is not that accidents happen. It is that in March 1984, choice to control the narrative may have prevented escalation. Sometimes the cover-up is not the scandal. It is the survival strategy.